Yeah, the ocean's been lying to the Navy for decades. Let's get into it. Number 10. Fast mover. You're hunched over a green-lit console 300 feet below the North Atlantic. A contact appears. It shouldn't be moving that fast. You try to lock a bearing. The echo sharpens for 2 seconds and then smears across the scope like wet paint. Gone. No track. No speed measurement. Just a ghost that outran your instruments. Sonar men call it a fast mover. Veterans swap these stories the way fishermen talk about the one that got away. Except sonar doesn't exaggerate. The machine prints what it hears. Here's what usually explains it. The ocean stacks layers of warm and cold water like invisible floors. Sound hits those layers and bends. One submarine can look like three. A school of tuna can look like a torpedo. A gas pocket near the seafloor can belch out an echo that races across the display. Multipath propagation. It's the culprit about 80% of the time, but that still leaves the other 20. The Navy's own declassified logs include contacts where two separate submarines tracked the same fast mover on the same bearing at the same time. Different ships, different arrays, same impossible speed. No propeller harmonics, no cavitation, no wake. Just a clean tone that moved faster than anything with a propeller should, and then stopped existing. Most fast movers earn a boring explanation after a week of analysis. A few sit in files that nobody has closed. Draw your own line between trick of physics and something we haven't built yet. Number 9. Bloop. 1997. A network of Cold War hydrophones strung across the Pacific picked up a sound so powerful it registered on sensors more than 3,000 miles apart. It lasted about a minute. A single ultra-low rumble that rose and then stopped. The team at NOAA's Pacific Marine Environmental Lab in Newport, Oregon gave it a name, Bloop. The internet loved it. Forums exploded with theories. Giant squid, undiscovered whale, underwater volcano. The wildest guesses got the most clicks. The scientists did something less exciting. They compared the waveform to every acoustic signature in their library. Earthquakes didn't match. Volcanic tremors didn't match. Ship engines didn't match. What did match was ice, specifically a large Antarctic iceberg fracturing and its keel scraping the continental shelf. The frequency profile and the duration lined up. Later fieldwork near the Bransfield Strait found similar signatures when ice calved and grounded. Case closed? Mostly. The primary signal fits glacial activity. But a secondary feature in the recording, a brief overtone spike around the 40-second mark, didn't fit the ice model. It's small. It might be an artifact of the recording equipment. It might be sympathetic resonance from a nearby ridge. Nobody went back to settle it because there wasn't enough funding, and the spike wasn't dramatic enough to justify a ship. That's the real lesson of the bloop. Not monsters, not aliens. The real problem is that ocean acoustics runs on a shoestring budget, and the deep doesn't wait for us to be ready. Number 8. False bottom. You're about to learn that the ocean floor can lie to your face. A sonar sweep returns a solid floor at 600 feet. The chart says the real bottom is at 4,000. Something in between is dense enough to bounce every ping back like concrete. It isn't concrete, it's alive. Marine biologists call it a deep scattering layer. Dense mats of jelly-like creatures and lanternfish migrate up at night and down at dawn. Billions of tiny gas-filled bladders act like a mirror for sound. During World War II, this confused every submarine crew in the Pacific. They thought the ocean had a second floor. In 1963, the crew aboard the research submersible Trieste dove straight through a false layer near the Mariana region. Above the layer, their sonar showed solid bottom. They descended through it and found the real seafloor still 2,000 feet deeper. Objects underneath were invisible to ships above. This is not just a curiosity, it's a tactic. A submarine captain who knows where the layer sits can tuck the boat underneath and vanish. Surface ships pinging from above see a floor and stop looking. The fix sounds simple. Switch frequencies. A low-frequency ping lights up the false layer. A high-frequency ping punches through it. Use both and you see the trick. In practice, it's harder. The layer moves. It rises at sunset and sinks at dawn. Weather and current and season shift it by hundreds of feet. What worked at noon fails at midnight. The sea doesn't just hide things. It builds walls out of living creatures and dares you to look harder. Number 7. Train. Imagine a cello note that never stops. That's train. Hydrophone arrays in the raw sea first caught it in 1997. A low, steady hum that went on and on without a break. Not a whale song, not an engine, something in between. The name came from the sound itself. It had the rhythm and grind of a freight train heard through a wall. Steady, mechanical, relentless. NOAA's acoustic team ran it against their ice library first. Large icebergs drag their keels across the continental shelf and produce long, grinding tones. The SOFAR channel, a band of water around 3,000 feet deep where sound travels farthest, can carry that grind halfway around the planet. Some train recordings matched iceberg drift tracks perfectly. The timing aligned with satellite images of massive tabular bergs near the Ross ice shelf. Case by case, those ones closed. Others didn't close. 3 recordings from 2001 showed a train signal when satellite imagery confirmed no large ice was present in the source area. The frequency was similar, but the harmonic structure was cleaner than any scrape should produce. One researcher at Scripps compared it to a standing wave resonance inside an underwater canyon. The geometry of certain trenches and ridges could theoretically amplify ambient noise into a pure tone. It's plausible. Nobody has confirmed it. For a submarine crew, the problem is immediate. A persistent low hum can mask the faint whine of a diesel boat on battery power. Operators call it hiding in the furniture. The hum becomes wallpaper. A smart adversary times a transit to match. That's why the train matters even without a final answer. It isn't just a sound. It's cover. Number 6. Quack. For almost 50 years, the Southern Ocean had a duck. Hydrophones near Antarctica picked up a repeating sound, a low rhythmic quack, and nobody could explain it. Sailors called it the bioduck. Scientists filed it as unknown biological or mechanical. It showed up near the ice edge in winter and disappeared in summer. Every few years, someone offered a theory. Ice cracking? Distant machinery? A species of fish nobody had cataloged. None stuck. The bioduck kept quacking and kept dodging every explanation. Then, in 2014, a team from the Australian Antarctic Division did something nobody had done before. They attached acoustic tags directly to Antarctic minke whales. Small suction cup recorders on the animals' backs captured their calls in real time. The match was exact. Minke whales produce a low, repetitive pulse that sounds like a mechanical quack. When the tagged whale called, the hydrophone a mile away recorded the bioduck signal at the same instant. 50 years of mystery. One suction cup. The solve matters because it shows what patience and the right tool can do. Decades of speculation got nowhere. One field season with direct tagging closed the file. It also raised a practical question. If one common whale species fooled the world's best listening networks for half a century, then what else in the ocean is making sounds we've already filed as unknown that simply belong to an animal we haven't tagged yet? The quack was solved. The bigger question it opened isn't. Number 5. Spherical plunge. 2 Navy pilots are on a routine patrol over open Pacific water. One of them spots a dark, round object falling from high altitude. No contrail, no wing surfaces. It drops in a straight line and enters the ocean without the splash you'd expect from a hard impact. They mark the coordinates and radio the ship below. An hour later, a sonar operator aboard a nearby destroyer picks up a faint return at that same position. One brief echo, no propeller signature, no bubble trail. Then the contact disappears. Cameras on the aircraft captured the fall. Surface radar tracked a descending track that ended at sea level. Sonar caught something at the entry point. 3 different sensor types pointed at the same spot at overlapping times. The investigation hit walls fast. Sonar buoys dropped at the location heard nothing after the initial return. An autonomous vehicle dove to the area and found open water and scattered plankton. No wreckage, no debris field, no chemical residue on the surface. Analysts tested the simple answers first. A weather balloon can drop and sink. Sun glare on the canopy can fool a pilot's eyes. A timing lag between the aircraft camera and the ship's sonar clock could make two separate events look like one. Each of those answers solved a piece. None solved all three sensors at once. Here's the engineering problem. Any object that crosses from air to water must survive a brutal density change. It's like hitting a wall at speed. Known weapons that do this, torpedoes dropped from aircraft, are built to handle the impact, and they're loud on sonar. This contact was quiet. That's what puts transmedium reports in a different filing cabinet. They don't just resist one explanation. They resist the physics we're comfortable with. Number 4. Slow down. A tone enters the hydrophone feed so low, you feel it more than hear it. Over the next 7 minutes, it drops in pitch like a record player winding down. Then, silence. NOAA recorded several of these events in the late 1990s near the Antarctic plate. The team called them slowdown. The sounds traveled through the SOFAR channel from sources estimated at thousands of miles away. The leading explanation is ice. When a large ice sheet flexes before a fracture, the stress release can produce a tone that drops in pitch. As the crack spreads, the frequency falls. Physics predicts exactly this shape of sound. Several slowdown events matched ice activity confirmed by satellite. The timing and direction lined up with fracture zones on the Ross and Ronnie shelves. But two events recorded in '97 didn't match any ice movement. The bearings pointed to open water south of New Zealand. Seismic stations showed no earthquake activity in the area. Ship traffic logs were clean. One hypothesis is geological. Submarine volcanic vents can release gas in pulses that produce tones that drop as the flow decreases. It's hard to confirm because nobody had sensors close enough to the estimated sources. For sonar operators, the practical concern isn't the mystery, it's the mask. A long tone in the low-frequency band can sit right on top of a diesel submarine's acoustic signature. By the time the slowdown fades, the sub has moved and the window is lost. Commanders learn to treat these events as both noise and opportunity. If a natural sound can mask a submarine, then a submarine can also choose to move during that natural sound. The ocean doesn't just make strange noises. It hands out free cover to anyone who pays attention. Number 3. Crash scar. The side scan image looked like a claw mark dragged across the seafloor. A bright white gouge 1,200 feet long cut through soft sediment and water too deep for any anchor chain. The survey team aboard a NOAA research vessel flagged it immediately. The acoustic shadow was sharp, and the backscatter was strong. Something heavy had scraped the bottom and left a clean trail. They sent down a remotely operated vehicle. The cameras found a shallow trench in the mud with exposed rock underneath. Coral had already started to colonize the edges. No metal, no paint flakes, no hull fragments, no fuel residue. Geologists offered two explanations. First, a turbidity current. That's an underwater landslide of heavy sediment. It can carve a groove that looks violent but is just gravity and mud. Second, in polar regions, large icebergs with deep keels can plow the bottom for miles and leave scars that look fresh for decades. Core samples from the trench told an older story. The sediment layers at the bottom of the gouge were consistent with a single, rapid displacement event several hundred years ago. Nothing recent. Here's the catch. Side-scan sonar makes old scars look new. The acoustic contrast between exposed rock and surrounding mud is so high that a 500-year-old trench lights up on screen like it happened yesterday. This is why experienced operators treat sonar images as clues and not as photographs. A sonar return tells you something is there. It doesn't tell you when it happened or what caused it. The ocean floor is covered in marks that look alarming and mean nothing urgent. The skill isn't in seeing them. It's in knowing which ones deserve a robot and which ones deserve a shrug. Number 2. Arctic fast contact. Under the ice, the rules change. A submarine beneath Arctic pack ice lives inside a sound tunnel. The frozen ceiling above and the cold, dense water below create a duct that channels noise with brutal efficiency. A whale call from 50 miles away arrives crystal clear. A pressure ridge groaning overhead sounds like it's inside the hull. In this environment, sonar contacts are both sharper and more deceptive than anywhere else on Earth. A crew on patrol beneath the Beaufort Sea reported a contact that closed from long range to near range in under a minute. The bearing was steady, the signal was clean. No propeller harmonics, no blade rate, just a smooth tone that moved like nothing with a screw should move. They went to ultra quiet. They changed frequency. They angled the towed array down and then up. On the second sweep, the contact had shifted 40 degrees in a time window too short for any known submarine or torpedo. Aircraft above dropped sonobuoys through leads in the ice. Two of them picked up the same bearing simultaneously. That's harder to dismiss than a single sensor glitch. The most likely explanation is an acoustic mirage. Arctic ducks can bend sound around curves of cold water and make a stationary source appear to move. A bearded seal calling from under ice can sound like a fast contact if the duct geometry shifts mid-call. That explanation handled most of the data. It didn't handle the two sonobuoys. Their bearings were consistent with each other and with the submarine's track. 3 platforms all fooled by the same mirage at the same time is possible in theory, but unusual in practice. The crew logged it as an unresolved contact. It joined a thin file of Arctic anomalies that nobody has explained and nobody has declassified. Under the ice, you hear everything and trust nothing. Number 1. Transmedium contact. Everything in this video has lived in one world: sound in water, echo in the deep. This last category breaks that boundary. A pilot watches a dark sphere descend in a straight line and enter the ocean. Seconds later, a submarine operator 50 feet below the surface picks up a bearing in the same direction. The timing overlaps. No splash signature, no breakup noise, no propeller tone on entry. Surface radar tracked a descending object that terminated at sea level. The aircraft's infrared camera showed a cool object against warm sky. Hydrophones recorded a single clean pulse and then nothing. 3 sensor domains, radar and infrared and acoustic, pointed at the same coordinates within a window of seconds. Analysts checked for timing drift between systems. The clocks were synchronized within 200 milliseconds. Simple explanations were tested and some fit partially. A falling weather balloon can drop without a contrail. Ocean clutter can create a phantom sonar return. A whale call near the entry point could coincide with the visual event. Each explanation covers one sensor. None covers all 3 at once. The engineering question is what makes this one different from every other entry on this list. If an object crosses from air into water with minimal acoustic disturbance, then it either has no mass worth mentioning or it has technology that manages the density transition in a way no public engineering paper describes. That's the honest line. We don't know. Navies have responded by building sensor networks that fuse radar and infrared and acoustic and satellite data into a single timeline. The goal isn't to name the object. The goal is to stop arguing about whether the sensors agree. Most of these files are classified. Most of them may stay that way. What they've already changed is how militaries think about the boundary between air and sea. It used to be a wall. Now, it might be a door. Whether anyone has walked through it is the question this video can't answer. But the data says somebody should keep asking. Sonar.